think the pen still works out there, but we'll go ahead and okay. Well, your timing is just perfect. Since I was running late. That there. Okay. Again, these are stolen slides. I'll post them on there. I'm going to be starting a new topic. I will revert back and review motors again, and probably hit robotics again toward the end. And probably hit a few topics. What I posted on the, I feel like I yell when I talk, but that's because I'm using this microphone. It's not so sensitive. You have the midterm exam, and that's due, as I recall, sometime this week. Is that right? That's there. That midterm exam has on it probably a version of all the problems that are going to be on the final exam in the robotics area. So that there, look at that midterm exam as kind of a study guide for 3 of the 5 problems on the final exam. Now I don't guarantee that those 3 problems are exactly like the 3 problems on the final exam, but the final exam will have 3 problems on robotics and 2 problems on PLCs. So, and you're going to see a version of all the problems ahead of time. So, the topic I'm talking about now, introduction, is PLCs, which is the latter part, because the title of the course is Automation and Robotics, and PLCs falls under that factory automation problem. That there. So, some of you might have had better and more in-depth courses in PLCs where there was a physical lab, and you did that if you had it, especially those that came from BMI into iQual. Right there. This is kind of a short 3 or 4 week introduction. I don't know how long we got left in the semester. It's not a huge amount of time. So right there. So I'm going to jump into that there. And I was asked the question whether I was going to have class today, and the answer is yes, I definitely have to. Oh, this has got. Oh, let's kill this animation crapola. That their animation slideshow, play narrations, use timing, turn all that stuff off right there. At there. So hopefully. Transactions, sound, whoosh, no sound. Right there, okay. Right there. Okay, hopefully that gets rid of all that fancy stuff. Someone spent, well, it's still got it. All right. Play narrations, we don't want this stuff here. Let's no animation, duration. All right. If this doesn't clear it up, I'm just going to go through and just advance the slides this way. That there. So okay, this basic set of slides actually talks about the basic hardware and software components. We're going to be using a software program which I'll introduce later on. There should be a version of this that you can download and install it on your PC. I'm having trouble installing it on this PC, so I may have to go back to my old laptop to do the simulation that's there. I actually purchased the software, but the way it works is you purchase it and it's only good for one laptop, and my old laptop is dying on me. Unfortunately, I get about 15-20 minutes out of the battery, so that's why I quit using it for class. But regardless, we're going to be looking at what's called a programmable logic controller. These have been around, and I don't want to get into too much detail, since the 1960s, early 70s. That they're still the #1 way that factory automation is done, and actually robotics are controlled by PLCs, but they also control the assembly line, pumps, valves. They control everything in basically a process control type system right there, which process control means that we're controlling a process. And manufacturing of an automobile is a process. Converting palm berries into palm oil is a process. Converting raw petroleum out of the ground into petrol that you can put into your car is a chemical process. These are all controlled by programmable logic controllers right there. So that's what this next couple of weeks is going to talk about, and we'll do some labs. There'll be virtual labs with the simulation right there. So the objective for this set of slides, which is pretty much the objectives for the next couple of weeks, although these sets of slides will only kind of touch on this. I'm going to go through these slides today and probably just start at Thursday, and then we'll go through and start doing some labs out there. So we'll look at the history. I'm going to use something called relay ladder logic right there, simply because that's the way I know how to program PLCs, and that's what I've used in industry. Did you use, those who took PLCs through BMI, did you use a different technique? Did you use a programming language, or did you use ladder logic? What? Don't know, don't remember. You slept since then, huh? You've gone home and eaten your mother's cooking. So, all right, well, we're going to use ladder logic right there, and you'll see what it's meant by ladder logic. And we're going to look at the input-output systems, the programming and peripheral devices. We won't get into that much detail other than know what they are. They're the same ones that we use for microcontrollers, same ones that you use for inputs and outputs, that control robots. That they're programming concepts. We're not going to get into that much other than how we enter a ladder logic and how we test it. We'll look at a few applications. During the final exam, you'll be asked to design a couple of systems troubleshooting and maintenance. Since we have no real hardware, we're not going to be able to do that particular portion right there. All right, PLCs, prior to PLCs, we used something called relay logic. And back in even the early 1980s, when I went to work for Magnavox, a lot of the test equipment that we worked on out on the factory floor, and even the factory floor, we used relay logic. And relays are basically devices that you can turn on or off, like a large transistor, and you can do timers with them, and you can design systems using relays. Now, relays are large. They consume a large amount, a considerable amount of power. They're prone to hardware errors. The term debugging, you've heard the term debug a computer program. That actually goes way back when computers were made out of relay logic. And the term debugging actually meant going through all the relays in the computer system and looking for insects that have crawled into the relays and caused the relays not to open and close properly. So actually the term was originally used by General Hopper. She was Admiral Hopper. She was in the Navy. I shouldn't move her to the Army. She was in the Navy back in the 1950s, and she referred to the process when they discovered that one of their computer programs was malfunctioning because a moth had gotten into one of the relays. So relay logic has some issues out there, but PLCs remove the idea of relays out there. And the main thing is that it's faster in hardware. Back in the days that we used relay logic back at Magnavox, we had to actually take the test equipment offline and rewire the relays and reset the timers manually on the relays. There was timers on that there, and it was a pain in the neck. It was an absolute pain in the neck. One of the test stands that I worked on was something called a pressure vacuum system. that would pull a vacuum on a sounding buoy to test to see whether or not the seals were properly done, because sounding buoys that you drop in the water is full of water. I hate to make that joke, but water leaks into a piece of electronic equipment, it usually does bad things. So we had to make sure that our buoy was waterproof right there. And not all electronics is waterproof. Even today, I lost a phone a couple of years ago, and I was walking out in the water there on a beach, and a nice wave knocked me down in my bag that I normally carry. This bag here, only it was a different bag at that time. That there, I got filled with water, and my phone and my tablet PC happened to quit working. So we didn't want that to happen to our sounding buoy. So we would test them. The way we would test them is we would turn on the vacuum pump, leave it on for so many seconds. We would measure the vacuum, the level of vacuum inside of our sounding buoy. We'd also measure the level of vacuum inside of a reference buoy that we knew was good there. And we would look for any change in pressure between the two of those. If the pressure went up in our reference, in our test buoy, we knew that we had a leak. So we did all this with relay logic. This particular test stand was built back in the 70s. It was determined that the time I was working on it was in the 80s, and we were having all kinds of failures for some reason. And the failures had nothing to do with the logic. I determined after about 3 months of digging into it. But, it was one of those stands. It was an old stand, been around for a while. And it was all done with mechanical relays. Well, while I was at it, I converted it over to a PLC type controller versus relay, simply to make it more reliable right there. So again, there existed factory automation before the time of PLCs right there. A most common example of relay logic is the standard stoplight today still uses PLCs out there. Why most of them change, or not PLCs, but a lot of them still use relay logic right there. Oh, right there. So developed to replace relays, cost dropped and become popular by the 80s. Now they're used in probably 90% of factory automation designs right there. 95%. Relay logic really has disappeared for the most part, but relays are cheaper if you have a very small system. PLCs will cost you several thousand ringgits just for a basic one. We'll see that. They're not really cheap. Microcontroller controllers are cheaper for smaller systems, but then you have to deal with the fact that you have to design it all from scratch. So PLCs are really quicker because you can just grab one off the shelf, plug in your modules, and run with them. If you grab an 8051 board or a Raspberry Pi or an Arduino, you have to write all the software. You have to design all the hardware interface equipment. That you're trying to run a factory floor. You're running some large motors and some large currents, and obviously a little Arduino that runs on 3.3 volts. You have to have quite a bit of interface hardware to that there, and that takes time and takes some engineering talent. PLCs are quicker, but they're a little bit more money up front right there. So, right there. And I'm going to try the slideshow again and see whether or not this thing is going to. Okay, at least it stopped the sound that there. So at least I don't have that annoying sound that there. Okay, the hydraulic division of General Motors, hydromatic division. I don't even know if the hydromatic division still exists today right there. I mean, it's, I never worked for General Motors other than I taught a couple of workshops in their factory for some of their electricians and their technician people, some of their automation people actually, or the technicians out there. As a matter of fact, I taught a course on introduction of PLCs from an engineering standpoint out there many years ago at one of the truck factories in Indiana out there. So I'm familiar with General Motors, but I've never worked for them as an employee out there, just as a contractor. But the first design criteria was back in the late 1960s. They wanted to get rid of relay logic right there. Now, General Motors is a big company that makes automobiles. They also make refrigerators. They own a company called Frigidaire, for example, that owns Electrolux, and General Motors, actually, their refrigerator and appliance department's owned by General Motors now. So they're into other things other than automobiles. But what they're most noted for is automobiles. And they sell a lot of cars. Even in Malaysia, you'll see a lot of Chevrolets. You know, that's owned by General Motors. They also own Buick, Cadillac. They used to own an Oldsmobile they've discontinued. They also make military hardware, although the Jeep was owned by Chrysler. I don't know who owns Jeep now, but they make cars and they make a lot of them, and they make them in different places. So their goal was to eliminate the high cost due to inflexible relay control systems. One of the reasons that General Motors was so keen to come up with an automated system that was very simple is that, unlike the MyV that has been pretty much unchanged for the last 5 to 7 years, right? My wife's got a MyV. I mean, it's a great little car. I mean, I really, it's dependable. It's kind of fragile. If you hit a curb, you end up breaking the shock or something like that. It's not what I call a heavily built car, but it's inexpensive and it's easy to park in KL. Peridot is probably between the local manufacturers, I like them better than I do Proton, but that's just my personal preference. I had a Canchel back in the 1990s. Any of you remember the Canchel? Tiny little car, that there. And of course, I'm a big guy, so I got a lot of abuse from people, for driving that tiny car. But it was the greatest car to park, right there. Now I ride a Vespa. It's much easier to park. Although since my stroke, I don't ride it as much as I used to. I'm still getting used to riding it. And I don't take it back and forth to work because I don't trust my reflexes on some of these crazy drivers that there. And there are their share of them that there. So, but one of the problems with American manufacturers, and what I was getting into before I got sidetracked, is that back in the 1980s and 1990s, and that the American consumer expected a new looking car every year. You don't find that so much with the Asian and the European manufacturers. I mean, because if you look at a BMW from 1995, you look at a BMW from the year 2000, and you look at a BMW today, they haven't changed drastically. I mean, they changed some, but not drastically. But for whatever reason, American car manufacturers and the American consumer was probably one of the most fickle, wanted something new and innovative every year, practically. Which meant that factories had to close down and retool for the next model year. Because the fenders had to have a different shape, the headlights were, they were oblong last year. This year they're going to be square. I mean, they were changing them every year or so out there, which created a huge expense for the automobile manufacturers in terms of having to retool their equipment, redesign their factory layout and how things were done. Sometimes they would eliminate components. We don't need this feature. Sometimes they would add new components, such as electric windows were added at one point. That's there. I remember when the automated windshield, the time delay for the windshield wiper came out, for example, and that came out in the 1970s, right? But this was during a period where there was a rapid change in, that there. They don't do that so much anymore. They kind of follow the European and the Asian, path where they make minor changes, and it's more of a progression, and it's not a huge radical change every year that there. And sometimes some model years they won't change from year to year. I look at a MyV that's 4 years old, and I look at my wife, and there's some very minor differences right there. I could pop the engine out of the one 4 years old and pop it into my wife's, and it would work perfectly fine right there. Just don't pump into a curve, otherwise you got to put a little, what do they call that, clamp on your, hold your fender on? Yeah, because my wife had to put clamps on her fender there. Evidently you can't replace the fender mounts that hold the fender in place, so you have to, put a little clamp externally to hold the fender in place. Kind of laugh about that, although I got a place on my also that I've got to put some clamps on too, probably. But as I said, they have a thin body. The design comes from a Japanese company. I can't remember it, but it's not a well-known Japanese company. What's that? It's I can't remember, but the company doesn't sell in the U.S. because they're known for very thin bodies that are not very, they don't pass the crash tests out there. So they sell them in Asia pretty much, but they sell them under the Perodua name in Malaysia. And I'll remember Paso is the name of the MyV in by the Japanese manufacturer, but I can't remember the name of the company. But so again, the idea is this is a modular form, and we can easily plug things in and out of them right there. So that was the whole thing about PLCs. We had a controller, we had I/O modules, we had timer modules, we had all kinds of various modules, and I don't know if I can write on this right now. Nope. If I circle the word repair, the circle comes out some way. For whatever reason, PowerPoint doesn't like my pen, so I might as well set it aside. It doesn't. I can't use it. Okay. That's it. So the control system also needs the capability to pass data to a central system. The General Motors system that I've seen, and I've been in the General Motors PLC lab or control room there at the Fort Wayne truck plant, and I've looked at their system, I've talked to their engineers, and every PLC on the factory floor is interfaced or networked to a much larger system in the factory control room. So they can reprogram PLCs from the engineering office at there. They can collect data from the factory floor. They know how many trucks have come through. They can tell the PLC that we want to switch from red trucks to green trucks. That there, and that's a fairly simple process. You just simply change the paint and the primer and the system. But first, you got to go through a flushing process to clean out the old paint. You don't want a red-green paint. You don't want it changing colors mid truck. That there, although that might be a popular truck, they're having a half red and half green. But regardless, the Christmas special. But regardless, you need the ability to pass data collection to a centralized computer. Originally, they had not envisioned being able to reprogram the PLCs remotely. The early PLCs, you walked out on the factory floor with a programming module, and you plugged it in the PLC and you uploaded your data, your program. Similar to the way we're going to do in the lab, only that in your lab we're going to be doing it as a simulation, not as real, right there. The system had to be reusable. One of the problems with the relay logic is that you unsolder and resolder a relay board enough times you throw it in the trash. And usually the process of unsoldering and trying to reprogram it, they usually end up just scrapping it because it was too expensive for engineering and technician time, and too prone to mistakes. Right there. Yeah. I remember back when we used to use a technique called green wire for doing early prototypes. And what green wire is you'd have a circuit board that had a bunch of pads on it, and you would solder little green wires from one pad to the other to connect your circuit. That was before our low-cost PC labs came out. Now, at least in the U.S., if I wanted to do a PC board, printed circuit board, I can upload what they call the Gerber files, and in 2 days, 3 days through express carrier for $20 US, I would end up with 5 boards with my design on it. So that totally eliminated the need to green wire. Here, I don't think they've got that capability. I haven't seen rapid turnaround custom PC board houses. They may exist. I haven't seen them. So I know at least the educational setting, green wire is still the way that most people do it. Or you use the prototyping boards where you move the wires. I've always just used a prototyping board. I don't have students solder in the classes I teach. But I know BMI does a soldering course, and I think they do a PC board layout course or something like that. That's there. I've laid out enough PC boards to say that I don't like doing it, but it's an unnecessary evil in the electronics world. But the whole idea is that they wanted something where they didn't have to do custom boards. Right there. They didn't have to do custom wiring. These old relays, if you looked at them, we had the relays on the top and the power transistors, and of course, Cordy won't see my hand. Underneath there was a nest of wires. It looked like a rat's nest or a bird's nest. If you ever look at a bird's nest and you try to pull out the individual twigs, it's a real mess. And that's what these relay boards look like underneath. So trying to troubleshoot and trying to reuse those boards and making small design modification was not an easy thing right there. So the method used to program the controller had to be simple enough that it could be easily understood by the plant personnel. This particular system is going to be implemented not necessarily by engineers, but by technicians. One of the things I noticed since I've been in Malaysia, there's not a huge technician workforce. There's a lot of engineers in factories that go out and program that. US labor costs are much higher. Europe labor costs are much higher. So we have a class of workers that are between the general worker and the engineer. They were called setup men or technicians or layout people. When I worked as a general foreman back in a company, I had a group of men. I'd have one guy that worked for me in a particular part of the plant, and he was a setup man for Department 23, and his job was to change the configuration of various machines to run different components. And that's all he did. He didn't run any production work. We had someone else that would change the setup for a different part of the plant. And this was a labor, negotiated, we had a union, it was a union plant, there was a labor contract. And because I was considered management, I couldn't touch the equipment. They had one of those rules in place that management could not touch the equipment. It had to be set up and maintained by maintenance personnel and setup. So this equipment had to be simple enough that a non-engineer, somebody without a 4-year degree, somebody maybe not even with a 2-year degree, could go in there and take the design from the engineer and implement it into the system and understand how it worked and make adjustments, for the equipment to work properly. And I remember when I worked at Magnavox, I worked as an engineer in test equipment for a number of years, off and on, both as a contractor, part-time, and a full-time employee. And my technicians that worked with me, and I won't say they worked for me, they worked with me, a good technician made me look very good. A bad technician made my life miserable. So, kind of like the OR doctor who was doing surgery. You may not care as much about the skill of the doctor, but you want his nurses to be very, very skilled. That there. So, the plant personnel were a key player in this setup right there. So, 68, the idea came around. It uses a CPU. The earliest ones use a version of the 8080, which then became the 8085, the 8086, the 8186, 286, and eventually became, you know, the i7 processor. I can't remember what they call the newest version. Kirby Lake was the one before, but now Generation 8's out. But that their Intel was a big player in some of the early ones. They're not so much a player today. Right there. The early one, you know, the first one came out with that there had 1K of memory. Now, if you think about 1K of memory, how little that is. There's about 1 page of written text. If you look at it in terms of saving a Word document, it's about 1 page. Right there. The average cell phone today has, in terms of memory, about 1 gig. 1 gig is 1 billion instructions. A meg is 1,000,000. A K is 1,000. So this is this can hold 1,000 instructions. Your cell phone can hold 1 billion instructions. Right there. The new Samsung Note 8 has 6 gig of memory in it, right there. 6 billion instructions. I mean, that there. So if you can imagine how small this was. Now, 69, I was around. I was 13, 14 years old in 1969. So I remember 1969. And that was the year that, you know, that the man landed on the moon, the Apollo program, NASA's computer system to put a man on the moon was about as large as the floor in BMI. This whole floor, not this room, but this whole floor contained that. And it had about 128K of memory. So if you can imagine, you know, how much computer processors were, you know, how precious memory was and processing speed was. It had, and this has got the timer going on here, so I better talk fast, otherwise the slide will disappear. 128 I/O instructions. That's actually quite a bit for a factory floor. So, again, in 74, about 5 years later, and this was the year I finished high school, they started using multiple processors. Still in the 70s, we were still using 8-bit microprocessors. The microcontroller, as we know it now, had not come out yet. So it was the microprocessor. So you had to have all the support I/O chips. The analog digital really weren't that common yet. They had to be done on discrete components. So things were still relatively large in terms of the PLCs. But it was much better than it was still better than the counterpart with the relay logic. They came out with timers and counters, arithmetic operations. Oh, now we're up to 12K of memory. 5 years later, we're up to 12K, right there. So, and we're up to 1,000 roughly I/O ports. So, 76, the remote input-output systems were introduced. That was a big jump forward. Now, in 77, we weren't using the CPU, but we were actually using the microprocessors. So the early ones didn't even use a microprocessor, actually. I made a mistake with that sort of thing. They were using a CPU that was custom. That there. 80, intelligent I/O was developed. That was a big step forward. We'll be looking at communications, enhanced software, documentation. Personal computers is programming aids. So 80s things are starting to look like they do now. Low cost. Now, the term low cost is still a relative term. You know, when they're talking low cost, they're talking a couple of $1,000 USD. No, they're not talking 20 bucks. If you buy an Arduino microcontroller, you're paying what, about 50 ringgits. We're not talking that low cost. You buy a Raspberry Pi, it's roughly about 150 ringgits, 120 ringgits for a Raspberry Pi, but that's a full-blown computer system, right there, Raspberry Pi. So but again, Raspberry Pi doesn't deal with industrial loads. Networking at all levels, PLC, using SCADA, which is the term, and I can't even remember what SCADA stands for. Manufacturing engineers know it much better than I do. Okay. Now, I was just mentioning in 85, SCADA was introduced, and again, I don't even remember what SCADA stands for, and I don't really care to worry about it. I don't work in that industry. That's there. But SCADA is actually is actually a standard for interfacing PLCs. It's been around for quite a while. The manufacturing engineers that used to, I ran the manufacturer. Well, actually, it was the mechanical and industrial engineering technology department, along with that there. So we had, our industrial engineers understood this very well. I really didn't get that much into that there, but I've worked with SCADA compatible PLCs, but I've just never got that there. But the main thing is that's kind of where the standard has stayed today. You're talking, that's been 30 years ago, actually, 30 some years ago. And the standards that they're in, the technology hasn't changed that much. It's gotten smaller, it's gotten faster, it's gotten more robust. Well, it hasn't changed a great deal in 30 years. And that's a lot of things in the electronics industry that you're looking at today in the electrical engineering area. Some of that technology has not changed drastically in the last 30 years. I was fortunate that I lived through the massive changes. I remember black and white television. I remember the transistor radio that you carried around that, they used to advertise by the number of transistors they had. I remember those things. That there. But most of you were probably around when the iPod first came out. The first electronically music, and MP3s have been around since you've been born. The MP3's been around for a long time. It came out in the 1980s, late 1980s, early 1990s. The MP3 came out, and that became the standard. The CD came out in the late or the mid 80s. I remember when the CD came out, and of course now the CD's obsolete. But so some things like that change rapidly, but they haven't seen a drastic change. The basic smartphone keeps getting big, more capacity. The cameras keep getting better. The amount of music they hold keeps getting larger. But the concept of the smartphone hasn't changed in probably 10, 15 years, right there. So, and most of you grew up with a smartphone put next to you in your cradle practically. Not quite that bad, but my nieces and nephews definitely have, and grandchildren grew up with, grabbing mom's smartphone to watch cartoons in the car. So you grew up always with that technology. But, they didn't always, well, the PLC have gotten smaller, they've gotten cheaper, they've gotten more robust, but they haven't changed that drastically since the 1980s, early 1990s. So that's why when we're looking at the history, it goes to 1985 and stops. Because there's not a whole lot to report since 1985. Right there. There's nothing that, it's like the development of the modern motor, electric engine, electric motor, or even the internal combustion motor for that matter. That technology hasn't changed much in recent years. If you look at motors, the biggest change has been in the electronic controls or the microprocessor controls. The actual motor design itself hasn't changed drastically, right there. So there's been a lot of things that really have not changed, and this is an area right there. So programmable, this is a definition that came around in '78. A digitally operating electronic apparatus that uses programming memory for internal logic and instructions implementing. In other words, basically, it's a computer-based control system right there. So the main thing is what we're controlling is various types of machines or processes. So as you look at this, and again, I can't circle it right there, but all this, after the word uses, is simply defining a microprocessor-based system right there. So there's a big fancy term is that we're going to use some type of digital or CPU or microcontrol or type logic to control machines or processes. Now, when we talk about a machine, we're talking about a motor. We're talking about a conveyor belt. We're talking about valves. We're talking about pumps. We're talking about a process is a more complex thing. When I think of processes, I tend to think of chemical processes more than I do manufacturing processes, but a manufacturing process is also a process. The process of converting palm sugar to granulated sugar that you could put in your coffee or tea, if you happen to be Malaysian, Malaysians tend to drink more tea, is a chemical process. Some of it's mechanical, where you beat the crap out of the cane, and some you boil it, so you have to turn on heaters. Some you have to add additional chemicals. Some you have to do evaporation to remove water. But again, it's a process where things undergo a change right there. and PLC.
Like vending machine that combine the manual coffee.
Yeah, up there. So, you know, I'm one of these lazy people. I'm a lazy person. So you mentioned coffee. I've got a machine that I throw a pot in and I close the thing and hit the, but it goes through a process. Up there. It's got to take the water in from the tank. It's got to boil the water. It's got to inject the water through the pod. Again, the process of making coffee from coffee beans to coffee. You got to cook the bean first, roast it. Then you've got to grind it. That there, while you're roasting, you got to stir it. I mean, these are all processes, right there. And you know, some of you are from villages, compounds, where a lot of these processes are still done by hand, right? That there. The process of going out and getting rice from a paddy field and laying it out and drying it and separating the nasi from the paddy, that's still a very manual process. There. I guarantee you in Louisiana, where they grow a lot of rice in the U.S., and they actually grow a lot of rice in California too, out there. And out there, there's nobody out there picking that paddy by hand. Mm-hmm. In the process of converting that paddy to rice or nasi is a huge industrial process run by PLCs. So in a lot of ways, when we look at processes, we're not replacing relays, we're replacing human beings that did this right there. So again, we'll go through, and I usually end shortly thereafter with call for prayers, as you probably noticed that there. But we'll kind of cover a few more. I don't know where I'm at in terms of slides. Disregard that there. I'm only 12 slides in the 77. As I said, that there. But looking at the leading brands right there, Allen Bradley is the brand that I am most familiar with. Allen Bradley used to be a division of General Motors. As I said, General Motors broke that off. Gould, Monicon, I've used them. Texas Instruments, that's what, we had a company in town called Central Soya. It's Central Soya. And contrary to popular belief, Indiana, where I've lived most of my adult life, grows two things that there. And their number one crop is corn, which is used to feed cattle and pigs, right there. Usually the cattle get the grain and the pigs get the stalks or the cobs. You know, pigs tend to get fed the garbage of the food industry because they're dumb animals, they'll eat the garbage. There's a reason why they're prohibited, by the way. I think everybody in the room here doesn't eat pork, but they use all Texas Instruments. I never worked for them, but I had a friend of mine that worked for them, and I've been to their facility, and he showed me what they did. And actually, one of my former colleagues, he was a professor at Purdue, that didn't get tenure. He ended up going to work for Central Soya. But Indiana grows a lot of soybeans, so that's why it was called Central Soya. So our two number one crops is corn. And corn, by the way, is also processed a great deal through chemical processes. There's probably more corn used in corn oil and plastics and fuel than there is eaten as corn right there. So corn is one of those plants that gets processed a great deal. So when I think of chemical processes, I think of Central Soya, and I think of Cargill, which does a lot of corn work, and those were big companies in the Midwest in farm territory out there. And they tended to use a lot of Texas Instruments. General Electric is a minor player. Westinghouse. I've never seen a Westinghouse PLC, to be honest with you. I've seen Cutter Hammer, but not too much. Square D, I've seen a fair amount because we had a company that made heating and air conditioning systems I can't even remember the name of the company, but they were old. But the same parent company owned Square D. So and we actually, near where I lived, we had a Square D plant that made the PLC. So I've seen a fair amount of the Square D out there. They're not real popular. They just happen to be there in Indiana. They have a couple of plants, and Carrier Group. Carrier makes heating and air conditioning systems that there, and they also own Square D. So we had a Carrier plant that made the controls for heating, ventilation, and air conditioning. They call it HVAC. That's there, and they all use nothing but Square D controllers because Square D was owned by Carrier, right there. Siemens. I've never heard of Kako and Moeller, but I'm sure somebody in Germany probably has. Siemens is a big one. Festo is probably, I think Festo might be what BMI uses, is the Festo. I know that they're sold in Malaysia, right there. Toshiba, of course, is a huge player. Omron is a huge player as well. They're popular in the U.S. Omron. I'd never heard of those. Mitsubishi, of course, they make everything. Mitsubishi does everything from PLCs to automobiles to television sets. They don't make phones, but they make a lot of the ICs that go into phones. So Mitsubishi makes everything. Those are the big players. The areas that they're used, manufacturing, of course, is the number one that was designed for manufacturing. The food and beverage industry, again, that falls under the process control. If you go to F&N Beverage there in Shaolam, or the Coca-Cola bottling plant, that's there, or does Pepsi have their own plant here? I think they do. Pepsi, Mountain Dew, are made by the same company. If you go to any of their plants, they use a lot of PLC technology. That falls under the same area of process control, making corn oil out of corn, making corn syrup out of corn, making soy sauce out of soybeans. I mean, all these various things, making fish oil out of fish. These are all this is all that process control right there. Metals, the process of turning raw iron into steel. I personally have never been inside a steel plant. I've drove by many of them over the years. Gary, Indiana was one of the steel manufacturing capitals of the U.S. before the Chinese and Japanese companies kind of pushed away. They're still there, but they're much smaller. But Gary, Indiana, and Pittsburgh, Pennsylvania in the U.S. are the big steel manufacturing plants areas. And Gary, Indiana is just outside Chicago, so as I drove to Chicago, I'd see U.S. Steel off on the right side, and U.S. Steel was about the size of Subang Jaya at that time. It was a huge plant, huge plant, right on the southern tip of the Lake Michigan, right there, where the barges would come in from Minnesota with the raw iron out there. And I grew up in Minnesota, so I know about the iron out there. But metals out there. The process of making bronze change human out there. So I mean, this whole metals have been very important to the evolution of mankind, and the process of making new metals that were stronger and more durable has been a huge thing that the human race has had to develop. And now making steel in large enough quantities to where a company like Herradura can make thousands of cars a day, or General Motors can make millions of cars a day, all using rolled steel. You can't make it by hand like they did back in the 17th, 18th centuries. Right there. Power, the process of taking hydroelectric or hydropower from a waterfall or a river and converting that to electricity requires a lot of control. PLCs are rapid power controls right there. The binding operations, and we won't talk about the petrochemical. I've talked about that enough already. Right there. I think I'm going to stop at this point. One is my sinuses are plugged up and it's hard for me to talk, and I think I've talked. And I'm still at my 1 hour 55. I am pretty predictable between 55 minutes and 105, right? Now 65 minutes is where I end every lecture. That there. So